All right, welcome to the notes for lesson 1.6. Let me make those a little bigger for you. In this last section for chapter 1, we are looking into transforming our functions. So across the top here, you're seeing just some basic parent function graphs. Notice this is the parent function of a parabola. And again, the parent function is just what the graph would look like at its most basic form. So there's no other numbers thrown in. It's just a basic x squared graph. Here's just a reminder of what an exponential graph looks like, and just a couple trig graphs. You can do this for any graph. These are just 4 examples of what we could do. So here are some basic transformations that we could make to any graph. So we're starting out with just shifting vertically. So if you look right here, remember the parent function graph was just x squared. If I throw in a plus 2 outside, then it takes the whole parent function graph and it's going to shift it up 2 units. So the vertex was at 0, 0. Now it's at 0, 2. Took the entire graph and shifted it up 2 units. With the minus 2, it would just shift the whole graph down 2 units. Notice the difference between a left and right shift and a vertical shift. So anytime your number is attached to x, like this one is, it's going to affect your graph left and right. Anything that is not attached to x, like this, is going to shift your graph up and down. And that's generally true for all of our transformations. Could be a shift, could be a stretch, could be a reflection. If it's attached to x, it's going to affect the graph left and right. If it's not attached to x, it's going to affect your graph up and down. When it comes to the x left and right transformations, it's pretty much always the opposite sign of what you would expect. So when you see a plus 2, this would actually shift your graph to the left 2 units. And when you see a minus 2, it's going to shift your graph to the right 2 units. So, typically we would say, oh, plus 2, we're going to go right 2. But for the x's, it's the opposite of what you would think. For the y values, it is what you would think. So for the y values, when you see a plus 2, it does go up 2 units. And you're seeing just some side notes over here on the right of kind of what this would look like with an algebraic explanation. But usually this makes a lot more sense with the visual graphing explanation that you see here. So the ones you just saw up top were adding and subtracting. So now if we get into multiplying, these are going to stretch your graph either up or down or left or right. So if you remember, the parent function to the sine graph typically has a max at 1 and a minimum at -1. But when I multiply the entire function by 4, it's going to multiply my max and my min by 4. So now instead of going up to +1 and down to -4, I am multiplying those numbers times 4 to get the new max and the new min. So this is my vertical stretch. And again, I know this is going up and down because this number is not attached to x. This one is attached to x, so you'll see the difference. This thing will affect the graph left or right because it's attached to x. This one is not attached to x, so it's going to affect our graph up and down. Same thing right here. If my a value, if I am multiplying the entire function times 1/4, then that will be what I would multiply my max and my min by to get the new max and the new min. So this is actually shrinking the graph to 1/4 of its original max and its original min. And again, you can kind of see how that would affect the point values that you see right over here. So if I took any point in its original form, if I just multiply the y coordinate alone by my a scale factor, then that's going to give me the new coordinates for my graph. So some people like to do this algebraically, like the way that you see here, but you can also do this visually if you have a graph to work with. Again, this number is now attached to x, so I know it's going to affect my graph left and right. And like I said up above, it pretty much does the opposite of what you would think. When you multiply your x's by a scale factor of 4, it does not become 4 times wider like you might think. It actually becomes 4 times skinnier. So the best way to look at that is if I have a scale factor for my x's of whatever that is, it's going to be the reciprocal of that I would actually multiply my x coordinates by. So if I had a scale factor of 4, like this graph does, well then I'm going to multiply all of my x coordinates by 1 over 4 to get the new values. And then the opposite would just be true here if I have a scale factor of 1/4. Again, this is multiplied times the x, so I know it's going to affect my x coordinates. But again, I would just do the reciprocal to all of my x coordinates. So I'm taking all of my x coordinates, right, whatever the original x coordinates are, right here, and I'm multiplying them times 4 in this case to get my new values. So I'm just doing the reciprocal of what you would see there. So that's for multiplication. The last one you have to be familiar with, so there are 3. You had the transformation or the translations that you saw in the first one. Then you have the multiplication with scale factors. And the third one would be reflections. So keep this in mind as a parent function graph. But if I were to multiply this base times a negative, so now it's negative 3 to the x, we get a reflection. Keep in mind, same as true with these, if it is not attached to x, it's going to affect your graph up and down. So with this base of 3, if I multiply the 3 to a negative 1, then it's going to affect my graph up and down. But if I attach the negative to my x, like you see here, well now this is going to affect my graph left and right because it's attached to x. So right here, again, if you change the sign of the entire function, it's going to do a reflection across the x-axis, so it's reflecting up and down. But if you apply the negative to the x itself, now it's going to affect your graph left and right. So now it's going to reflect across the y-axis. So again, here was the parent function graph. You attach the negative to the x, and you get a reflection left and right across the y-axis. So here's some specific examples with some real numbers. So keep these numbers on your screen here or write it down as we go through a couple examples. So again, right here, if I subtract 3 from the entire function, again, this is not attached to x, so I'm going to apply this to my y coordinates. So I'm going to subtract 3 from all of my y coordinates. So if you look at the original y coordinates, so I'm going to subtract 3 from that 0, I'm going to subtract 3 from the 4, and subtract 3 from that 0, and that's going to give you the new coordinates that you see right here. So the one that was not written in, so originally was 8, 0, this would now be at 8, negative 3. This one is attached to x, and remember these do the opposite of what you would expect. So with a minus 5, I'm actually going to add 5 to all of my x coordinates. So that 0 would become plus 5, that becomes 11, that becomes 13. Notice the y coordinates did not change. I just added 5 to the x's to get the new image that you see here. Right here we have a scale factor. This is not attached to x, so I would apply this to only my y coordinates. But if you take all the original y coordinates and multiply them by a half, you get the new image that you see here. Notice the x's did not change, it was only the y coordinates. This one is attached to x, so I would apply this scale factor to my x coordinates only. And remember, for the x's, you do the opposite of what you would see. So instead of multiplying them times 1 over 2, I would flip that and multiply all of my x coordinates by 2. So if I did 0 times 2, I still get 0. If I did 6 times 2, I get 12. And 8 times 2 is 16. The y coordinates don't change. So this is the new image that you would see right here. Keep this in mind, I got to scroll down, but I'm still working with the same function that you see right here. So last couple here. So again, if you apply the negative to the entire thing, we're going to reflect the graph vertically, up and down. So all that would do is change the sign of the y coordinates. So if you look at the original coordinates that we had up above, and just change the sign of only the y coordinates, this is the new image that you would see here. This one is attached to x, so this would simply tell me to affect my graph left and right. So I'm only going to apply the negative to the x coordinates only. But if you just take the original numbers and just change the x coordinates to negatives, or just change the sign of the x coordinates, this is the new image that you would see here. So again, originally this was positive 6, 4. So I just changed the sign of my x, and now I have negative 6, 4. This is the best example to know, because this is what it would look like on a test. So this is everything rolled into one. We have a reflection here. We have a horizontal shift. We also have a vertical shift. So there's 3 operations going on within this one graph. It does matter which order you do this in. There are some cases where the order really doesn't matter, but just to be safe, like this one, you want to go from left to right. So if there's a reflection, do the reflection first, then do the transformation. So I'm just going from left to right. And again, anytime you see a reflection, do the reflection first. Sometimes that matters and sometimes it doesn't. In this case, it definitely does matter, and I'll show you the difference. So in this one, if you take the original function that we had up above, and I'm going to start by multiplying all of my y coordinates by negative 1. So I'm going to start by changing all the sign of my y coordinates. Then I'm going to add 3 to my x's, and then add 4 to my y values. So I'm just going in order from left to right, do the reflection first, then the transformations. And this is the new image that you would see if you did all 3 of those correctly and in that order. But again, I want to show you something really quick. If I had done the +3 and the +4 first, then did this last, I would get a completely different shape. So keep those numbers in mind for just a minute. But if I started by adding 3 and adding 4, and then doing this, watch what would have happened. So if you look at the original function right here, if I would have added 3 to this and added 4 to this first, I would have had the point 9, 8. Then if I brought in this negative at the end, so I would have multiplied my y coordinate times negative 1. So from 9, 8, I would have had 9, negative 8, and that would have given me a point way down here. But that's not what we get. See, if you look at how it was done properly, clearly this is not 9, negative 8. So the order did matter on this. So we did the reflection first, then did the transformation. All right, and the last part here, this is really the exact same concept. It's just in vector notation form. We're going to do a whole chapter on vectors later on in the year, but this is just a little introduction on what vector notation looks like. It's the exact same thing as an ordered pair, but it's written vertically instead of horizontally. So the item that you see on top is your x. The item that you see on bottom is your y. So here's the original graph that we have right here. You can see this is a parabola, and it would have had a vertex at 3, negative 7. But if I take this graph and I affect it with this vector, with vector notation, and this is key, with vector notation, you do not do the opposite of what you would think for the x's. You do exactly what you see here for both coordinates. So this one is telling me to subtract 5 from my x and add 11 to my y's. So if I take the original vertex, which was 3, negative 7, that's this one. Right? We call that a minimum because this parabola was opening upward. So the vertex was the minimum. But I'm simply going to apply the vector and subtract 3 from the x, add 11 to the y, and this would be my new vertex, or the new minimum. This is the same question but backwards. This is one you really want to know. This will definitely come up within testing at some point. They're basically just asking you which numbers do what. So here was the original graph. This is just a parent function parabola. And they're just asking you to identify which number does what. So we have 3 operations going on there. So they're first asking you what numbers were affected with the translation. So this would be the x change, this would be the y change, and then k is the scale factor. So they said the scale factor of k. So you're just identifying what those numbers are. So if I just go from left to right, well, here's the k value. That was my scale factor, so k would be 4. Here's the p value. And remember, if that's a +7, we would see the p-value as -7. And then here's the q value, or the y transformation. So if that was +8, then q would be +8. And so we're just identifying what those three values are as we see them within that setup right there.